recording. Okay, great. Thank you so much all for coming to today's webinar by Professor Mengxia Liu. And this is the fourth webinar by Yale PIs. Our goal is to introduce our excellent faculty and to find a connection with Korean industry partners for upcoming funding cycle from KIAT. So it's a great pleasure for me to introduce Professor Mengxia Liu. She got her PhD from University of Toronto and got postdoctoral training from University of Cambridge in UK. She has a number of awards, but one of the awards that I really want to highlight is this Packard Fellowship, which is given to only the very best young scholars across the entire science. So it's an extremely prestigious award that only very few people receive. That means she is a rising star. She studies this very interesting subject of like light-matter interaction, basically how the information from the light is converted to the electronic signal, which can be used for sensing and communication. So I asked her to give about 50-minute presentation. She's going to go through some of her exciting research on the solution process semiconductors. And after the presentation, we're going to have a short Q&A. And as I mentioned earlier, we are going to record this video and upload onto the KCITY website, and the KIAT will also distribute to you all. All right, with that, Mengxia, just go for it.
Okay, great. Thank you. Thank Jihong and KCT very much for offering me this opportunity, and also thanks Kiat for coordinating this meeting. So I'm going to talk about next generation sensing and communication. And what is very important is we want to use light as a future carrier for information. So in nowadays, light is not just for illumination. It is a very powerful way of carrying information across multiple domains. So, for example, in optical communication, we use light pulses to transmit vast amount of data. And we can use light for computing because optical approaches can promise a faster and low power processing through photonic circuits instead of electronic circuits. And also, light, especially infrared light, can be very important for bioimaging because light enables us to visualize molecular dynamics in real time. So what unites these applications is our ability to utilize light's high-dimensional information space. And let's see what is this high-dimensional information space mean. So today's optical system rely heavily on cameras and laser operating in the visible spectrum. So wavelengths is one of the information space. Although the visible is highly useful, the infrared part is also very important for communication, and for the mid-infrared, it is important for defense and biosensing. Although they are very important, but nowadays people lack of good light emitters and detectors that can fully control or generating the infrared light. And another dimension is polarization. Conventional systems control light's polarization using free space optics. And these free space components are very bulky and lossy, and they are also fundamentally unsuitable for integration. And our work instead focus on directly generating light and detecting light with controlled polarized state. In generating polarization controlled light, or generating a specific spectrum is only half of the story. We still lack of a sensing system that can simultaneously and accurately resolve the polarization and spectral information in real time. We want to have a way that we can tell the entire information of light simultaneously. So such a capability is very important for applications ranging from hyperspectral imaging, secure optical communication, and computing. So our goal is to develop some compact, high-dimensional emitting and sensing architectures that can generate and extract this multidimensional light information in a single shot. So I will structure my today's talk with three parts. So the first part will start with imaging and sensing with polarized light, using a novel material called hybrid organic-inorganic halide perovskite. And the second part will focus on infrared optoelectronics using colloidal quantum dots. And the third part, I will talk about collaboration and resources at Yale Engineering and Energy Science Institute. And at the last, will come with my summary of today's talk. Let's start with the imaging and sensing with polarized light. So before I give you the real projects we are working on right now, I want to give some examples of what a polarized light can do for us. So first is the defect inspection. This can be highly useful for semiconductor industry when producing the semiconductor like silicon wafers or manufacturing different semiconductor devices. Normal cameras are not very sensitive to contaminations or strings that generated during the production. But polarized light are highly sensitive to the refractive index of the material. So if there is a single touch from your fingerprint, if you get a fingerprint on top of a glass substrate using the polarized light, this a thin layer of oil molecule can reflect the light, the polarized light differently. So you will get a clear pattern or a clear image of your fingerprint. So this is the way how polarized light can inspect the defects during the manufacturing. This is the same for the string generated. And also people can use the polarized light to determine or to identify the material or substance. Another application is medical diagnosis. Um, a lot of tissue or cells or even human skin reflect polarized light differently. So using polarization, we can distinguish a healthy tissue versus a tumor. So this is a general way people have used in bioimaging. But in the past, bioimaging has always relied on very bulky systems. And our goal is to develop some new architecture that can reduce the cost and make the bioimaging more in the real time. Another application is in the astronomy. So people have been trying to use polarization to map magnetic fields swirling around the black hole. So all of these are the application with polarization. And our goal is first to generate the polarized light with some polarized light emitters. So there are two types of polarization. One is called circularly polarized light, and another is linearly polarized light. They're both very important, and the material we are gonna talk about today that used as the light emitter are organic inorganic halide perovskite. This is a type of material that have a cubic structure or near cubic structure where they have an organic molecule sitting in the A side with octahedrals sitting at lead halide octahedrals sitting at the four corners. This material have been used heavily for photovoltaics in recent days. And one significant properties of this material is its flexibility and tunability in their structure. By using different organic molecules, the structures can be completely changed from 0 dimensions to 3 dimensions. So 3 dimension is always called bulk material, and they can also be structured into nanoplatelets, nanowares, and nanocrystals. The bulk material is used for solar cells. They have very good electrical and also optical properties, but the nanoplatelets and nanocrystals, which have a very obvious quantum effect, they can be used for light emission. But usually they emit unpolarized light. So we try to figure out how to make them emit in the circularly or linearly polarized light. So one strategy is just to use the nanoplatelets because they have this geometry dissymmetry. They have a two-dimensional shape. In the lateral way, they have a lot of unit cell, but in the out of plane direction, they only have one or two unit cell. So this geometric dissymmetry allow them to get linearly polarized light. We also want to get circularly polarized light from these material, and the strategy is to add put chiral molecules on their surfaces. The chiral molecules are the organic molecules that have perfect mirror symmetries. They can bind onto the surface of these nanoplatelets and induce a chiral distortion in their octahedrals. And this allowed the perovskite nanoplatelets to generate a differential absorption in the circularly polarized light and also emit circularly polarized light. And furthermore, we want to find a way. We want to find a way to orient these materials because once we orient these nanoplatelets, we can align their electrical dipole moment. And if we get them fully standing on the substrate or make all of the nanoplatelets lying on the substrate, we will have an even stronger linearly polarized light. So this allows us to get a very large or enhanced anisotropy factor when we orient all of the nanoplatelets from mixed orientation to face down to edge down orientation. So this becomes a very highly tunable material system that can generate a highly tunable polarization. So it can tune from linear polarization and also with a combination of circularly polarized light. And this can be a very important system for 3D display and 3D imaging. But one drawback for this is the emission is always indivisible. So the emission we get here is in the blue range. We can tune it to get green or red in the future, but it's still very hard to get near infrared. So we want to target near infrared because that's a very important communication band. So we look at the existing materials that can generate polarized, especially circularly polarized light in the infrared, which is the only existing one is molecular lensnide complex. This is a material with a lensnide ion sitting within a distorted chiral molecular complex. This chiral molecular complex can absorb light and transfer the energy from the organic into the lens light center, and the lens light will emit light. And because of this distorted environment, the lens light will have their rotational strands opened by the chiral geometry. This will result in a circularly polarized light emission. So the existing material can reach the symmetry factor 0.17. I have seen an even higher number around 0.6 to 0.7. But the drawback of this material is they have very, very low absorption cross-section and low quantum efficiency, which means although they have a good degree of polarization, their brightness is very low. This is still not very good for using as a light emitter. So our strategy is we think if we can use perovskite as an energy transfer matrix to replace this lens night complex and dope the perovskite with the lens night dopants. And if we can have putting the chiral molecules on the surfaces, the chiral molecules can further distort the surface structure. So the lens night dopants can be located into a distorted chiral environment. This will mimic the structure or the mechanism of the molecular lens night complex. So if we shine light with the material, there is a very efficient energy transfer from the perovskite matrix to the lens night dopant and emit light from the lens night dopant. We have tested this material and the very efficient, highly efficient energy transfer has been proved. So this allows us to get a quantum efficiency above 100% in the near infrared. Using the dopant ytterbium and erbium, we can get emission in around 1 micron and 1.5 micron. And also, because this surface distorted lens night dopant, we get very high dissymmetry factor, around 0.24 in the near infrared and 0.36 in this communication band. What is more important is the brightness of this emission. So if we look at the brightness of the circularly polarized light, it is 3 orders of magnitude higher than what previously got from the existing molecular lens night complex. So this has been very important, can be very important for some industrial applications. So here is a summary of what kind of applications we can use. So first is 3D display and imaging. A polarized light emitter can allow us to encode left and right views in orthogonal polarization states. And if the receiver decode them with analyzers or polarization sensitive sensors, this will enable very efficient 3D display or imaging. Another is the optical is for noise-free communication. If we use a well-defined polarization as information, we can enable we can transport a lot of information for optical communication. And the last one is a polarization multiplex hologram. This means that when using a polarized, circularly or linearly polarized light to shine onto a hologram, we can generate different patterns. This allows us to store or project multiple holographic images using the same aperture by assigning each image to a very different polarization state. So this can be important for anti-counterfeiting or near eye display. So next, I will move to polarized light and high dimensional photo detection. So we just finished the light generation and we will start with the detection of the polarized light. If we look at the existing imaging and detection systems, polarimetric imaging have been used have been designed using a normal camera and put an array of meta-surface patterns. So these patterns allow to selective transport the linear polarized light. But these cameras are very expensive and they only have limited wavelength range because each of these patterns are usually related to a specific wavelength range. Another system, which is more complex, can tell us both the polarization and spectrum. So this is called spectral polarimetric sensing. They are always using very bulky systems with a lot of free space optics inside. They are very slow because they need to scan from one wavelength to another wavelength or one polarization to another polarization state. Also, they do not cover any spatial information. So none of these systems are ideal, and our goal is to develop some ultra-compact solution for real-time analysis of spatial polarization and spectral information. So we designed a strategy called algorithm-enabled optical sensing. Our goal or target is to design an optical filter that transforms arbitrary polarization and spectrum into a unique uh, optical pattern. So by having this optical filter, the incident light will be encoded with a specific intensity. So if we think about the light, incident light as a matrix, the high dimensional light field can be written as a matrix. And if each point in the filter has a specific property, and the matrix dot time the filter property will give us a transmitted intensity. This transmitted intensity will be read by the CMOS detector. If we design a filter with every pixel have a point-to-point variation, so each point will have a different transmitted intensity. This will allow us to generate a raw image, and all of the high-dimensional optical information are encoded within this raw image. By decode this raw image, we can reconstruct the full information of light. So this is our mechanism. And we try to develop some materials that can create this required property for the filter. So what is important is on each point, we need this transmission depends on all of the interest dimensions, for example, polarization and spectrum. And also we need to have a point-to-point variation. The first material we look at is, again, halide perovskite. But this halide perovskite has a very strong anisotropy, which means if you look at the material from along the b-axis versus along the a-axis, the material look very differently. So this give them a very unique property called linear dichroism, which means when the light have a polarization along a-axis versus b-axis, the absorption of the material is different. And also, because this material is polycrystalline, so each grain have a very different orientation. This means the a-axis of each grain is rotating, is different. This generates a point-to-point variation. Furthermore, we make this material with a chiral structure. So the material have a circular dichroism, which means they have differential absorption to different circularly polarized light as well. So with a different circularly polarized light, the transmission of the material is also different. So this material fits for all the required properties we are looking for. If we shine light onto this material with different incident light, different incident polarization, we can get completely different transmission mapping. And this, if we use these data to train a model, if we collect enough data, enough polarization and the transmitted pattern to train a model, we are able to use this filter to determine any unknown light. So we build a machine learning model using convolutional neural network. We use all of these input polarization and the transmitted pattern as to train the model, and this allow us to get a very high mean absolute error, which means we have a very, very low error when we and a very high accuracy when distinguish an unknown incident light. This is among the best of the MAE for many different materials type. And what is special for this material is it can reach a very low wavelength range. It can reach the blue and violet range, which is not very usual and not very easy to achieve by the meta surface. And also, we are able to make it into imaging using this material. So, okay, like this is how we use this optical filter or this disordered optical filter for polarimetric sensing. And up to now, we only solve the polarization state. But what we also want is spectral polarimetric sensing, which means we want to solve not only polarization, but spectrum as well. ProfSky does not allow us to do that, so we try to look for some new materials. And here, one type is called helical structure. So if we make the material into a helical pattern, it has a periodicity. And by tuning this periodicity, the wavelengths can be tuned. And this, because this helical structure and naturally have a differential absorption of circularly polarized light, because this helical structure can reflect half of the polarization, circularly polarized light if when the helicity match or mismatch with the helicity of the original structure. So we observe a very strong differential absorption in the circularly polarized light. But how can we generate the linear dichroism, and how can we further broaden this transmission? We try to induce spatial disorder. So if we increase the disorder in the periodicity, we are able to broaden the transmission wavelengths. And also, if we disorder in the in-plane direction by creating some tensile strain in the material, we are able to generating some linear component in the optical response. So if we look at a disordered film we created, the spectral response, we have very different spectral pattern when for the optical for the single film with different wavelengths of light. So we can get very unique pattern from each of the wavelengths. And also for different polarization, we get completely different patterns. This is simply by generating this order into this perfect helical structure. And it turns out allow us to get very different transmission spectrum for different polarization, and we finally make this into a spectral polarimetric sensor, so it can give under a uniform polarization. Under a single wavelength and uniform polarization, we are able to accurately resolve the polarization state. And also under a uniform polarization, for a given spectrum, we can accurately reconstruct the spectral information. What is very special and unique to this project and this material is we combine the polarization and spectrum. We can still tell the polarization and spectrum simultaneously with a very high accuracy. We further tested mixed polarization with a very broadband um, spectrum, and we can still keep a relatively good accuracy. This have not been measured by previous systems or previous compact systems. So some potential industrial applications, because this hyperspectral information will allow a lot of agricultural analysis, because like rivers or lands and different Earth surface will have a different response to the different color. So hyperspectral information are very important for agriculture, but the polarization is also very important for object identification. So the combination of polarization and spectrum will allow new information and new opportunities for agriculture industry. And furthermore is the bioimaging, because cells, tissues, or skins can reflect light can have different response under different color and different polarization state. So here is some examples of skin component reflecting light under different polarization and different color. And we can see that for uh, different places of the skin, we can have people can get very different response from the different color and different polarization. So if we can fully open the dimensionality space to use the light and detect light with full of information, we are able to get more detailed analysis for biomedical diagnosis. And some future goals that can potentially allow some new industrial applications are lensless high-dimensional imaging. So currently, all high-dimensional sensing is still rely on ultra-thin optical filter combined with a CMOS camera, and these are all required a lens. But for future applications, we want to fully integrate everything onto a chip. So a lensless imaging opportunity is very important. So we want to design some lensless high-dimensional sensors based on computational imaging method, so we can generate an ultra-compact solution in the future. Okay, now I will go to my second part, which is infrared optoelectronics for sensing using colloidal quantum dots. So infrared sensing has also covered a lot of applications. So for the shortwave infrared, one important application is autonomous driving. Cars need to communicate with each other, and currently the autonomous driving are using um, red light to communicate. And because infrared sensors are very expensive and infrared sensor response quite slow. But in the future, if we want to increase the accuracy and also the detection range, the communication distance between the cars for autonomous driving, using shortwave infrared light will be very important. And this requires the sensor to respond more accurately and also faster. Another application is blood sugar monitoring or glucose monitoring. One method is to rely on shining infrared light, and the infrared light gets scattered or reflected by the blood glucose and can be received by another detector. This requires a robust emitter and a robust infrared detector. Another application for the shortwave infrared sensing is for food uh, or agriculture inspection, because normal camera cannot detect a bad spot in a food or in a fruit or in the material, but this shortwave infrared light can tell it very easily. Furthermore, mid-infrared can be another very important spectral range because a lot of gas molecule absorb in this range. So in the industry that generate a lot of toxic gas, using mid-infrared sensor is one of the most accurate and accurate way to detect the toxic gas. For military, mid-infrared has been used for target detection. So all of these applications, followed by these applications is the materials we are using for infrared sensing. Quantum dot is one of the key material we use and work on. Colloidal quantum dot exhibit a highly tunable size and band gap because for a given size and given material, the band gap can be the band gap is highly dependent on the material and the size of the nanocrystal of the size of the quantum dot. This makes them very important for near-infrared and mid-infrared applications, but because simply by reducing the size of the material, we can reach longer and longer wavelengths. However, these materials have some limitation in their light emission and photo detection because their transport property is very bad. So we recently developed some strategies that can improve the conductivity of the material by using a method called solution phase ligand exchange. So this method can completely remove the insulating molecules kept on the surface of the quantum dot and replace them with very short ligands. And this new exchange method compared to the old exchange method can significantly reduce the disorder generated into the quantum dot film. And this method has been utilized on a lot of different type of quantum dots. And one successful result is to apply onto an indium arsenide quantum dot for a photo detection in the near infrared. So this generates a good photo detection range from visible all the way up to 1050, which is similar to the response range to silicon, but it has a much better detectivity compared to silicon and also a much better photocurrent response time, as short as 2 nanoseconds, which is very important for LiDAR applications. And also these quantum dot structure, if we want to put them in use for light emission in the infrared, we want to confine all of the electron holes into the quantum dot. So we embed the quantum dot into a high mobility perovskite structure and form a perfect lattice matching between the perovskite and the material and the quantum dot. So when shining light or injecting electron holes into the perovskite, the electron holes can be confined within the quantum dot and finally emit from the quantum dot. This allows us to get a pretty decent quantum efficiency and a very tunable electroluminescence, which is a very successful LED device. So a future goal for this application can be chip integrated design for in-sensor computing. So conventionally, data generated from sensors have to be reformatted and transformed and transferred to computing units. But in the future, if we can put everything integrated with the readout circuit, we no longer require the moving of the data, but to avoid a lot of problems and also reduce the energy to reduce the energy consumption. Okay, so the last part of this talk is the collaboration around Yale engineering and some resources at ESI, which is Energy Science Institute at Yale. So first, I want to briefly introduce my collaboration at Yale and beyond Yale. So Professor Peijun Guo at Yale Engineering is a spectroscopist who have done a lot of amazing work on photophysical understanding of hybrid semiconductors. And Professor Hailiang Wang at Yale Chemistry Department, we have been collaborated on a project generating artificial leaf for solar methanol production. Some other projects I have done with my important collaborators, Dali Sun and Jun Liu at NC State at university, is to understand the chirality-induced spin transport in the two-dimensional halide perovskite. And also with Gail Ong at UConn, we developed the quantum dot-based spin photon emitters. So I will spend more time on to discuss the collaboration with Professor Peijun Guo. He has recently developed a new methodology for tracking heat flow in semiconductor device. I'm focusing on the optical side of the materials. So he has got a lot of focus on heat generation and thermal properties in the semiconductor device. So he used a fully optical method to use an optical vibrational pump to generate the heat and use a visible probe to track how the heat flow in the material. Because when the heat is generated within the lattice of a material, their optical visible response to light is also changing. So Peijun is leveraging this phenomena to track and image the heat flow within the material. So here is an image showing how the heat is heat is flow or moving within several microsecond. So this allow us to resolve the heat flow in both spatial domain and also with a very high temporal resolution. And also because this method is fully rely on light. So this is non-destructive. There is no need for any transducer or no need for putting an electrode on it. And also this allow to understand how the device degrade in a very harsh environment. So here is a short video showing how the heat is generated and moved within the material with ultra-fast temporal resolution. So another opportunity or another application of using this spectroscopic method is to detect the defects in flexible electronics and semiconductor chips. So previously, like if we want to see the defects in the chips or in the flexible electronics, the way is to use cross-sectional SEM to see all of the cracks and defects. But these can be destructive to the sample itself, and also it only gives you a very small field of view. But if we use this optical method to see where the heat is localized differently within the material, we are able to track with a larger field of view, and also we can track the generation of these cracks in real time. So this can be very important for the future defect inspection in semiconductor chips. And also, Peijun have done excellent work using this all optical infrared detector and imagers. So still using this infrared light to generate a pattern and use a visible probe to detect. And because the visible probe can be reflected and get into the camera, and this is a way to track to image the infrared pattern. Some other optoelectronic researchers at Yale Engineering I want to introduce to you. For example, Professor Zhong Han at the ECE department. He is an expert in building blue emitting lasers. He is an expert in 3-5 semiconductors and blue emitting lasers, especially he demonstrate a nanoporous gallium nitride vertical surface emitting laser diode, which has significantly overcome the bottleneck for the gallium nitride laser diodes. And he has also create a lot of new method to grow and dope gallium nitride. For example, a selective area growth and doping for the power electronics. This is a new method he developed using some metal organic precursors to assist the MOCVD for the gallium nitride to grow. And at the last, I want to introduce some resources we have at the Yale Energy Science Institute. We have newly renovated lab space that are allow us to do all of these semiconductor and sensing research. We have a brand new and state-of-the-art aberration corrected TEM, which allow us to do all of these nanomaterial applications and research, imaging core, and a material characterization core for all of these optoelectronics and photonic research. So at a summary, we are fully ready and equipped for a productive collaboration on semiconductors, optoelectronics, and sensing applications. We are at a faculty at Yale Engineering and also associated with KCITY. I'm very happy to any type of collaboration or opportunities to interact with you. So if there are any opportunities, let me know and we can discuss in the future. So at the end, I want to thank my collaborators and my group who did all the work for these research and my funding agencies. Thank you so much.
Thank you so much, Mengxia. Excellent presentation. I particularly appreciate your effort in introducing some other colleagues at your area, also at the Energy Science Institute. We have time for any questions that the audience may have. And don't get disappointed, Mengxia. It's okay. I think in most cases we don't get a lot of questions, but I'm sure they
Mhm.
have a lot of questions. Hey, you guys are all welcome to send questions through the chat, or you can even speak in Korean. I will translate. But if not, don't worry. I left contact information for me and Junyoung Park, who is the KCD coordinator, and I also left website for Professor Mengxia Liu, and you are welcome to contact her for any scientific question, or if you are interested in collaborating with Professor Mengxia Liu, please do not hesitate to contact me. All right. Thank you so much for your participation. Thank you so much, Mengxian, for your presentation. I
Yeah,
guess you,
thank you. Thank you,
I,
Jihong.
I guess you are still suffering from jet lag, right?
Um,